Hello, welcome back, everyone. My name is John Morrow. I'm a professor of material science and engineering at Penn State University. The topic of today's presentation is about the Deborah number. The Deborah number is one of the most important quantities in the field of rheology and also critically important for my own specific area of research, which is in glass science. What I'd like to do with this presentation is to give you some history of the concept of the Deborah number because it does have a fascinating history. Then we will cover the definition of the Deborah number and discuss some of its implications, both from a physics point of view and from more of a philosophical point of view. So I would like to start at the beginning. If we go way back in time, the Deborah number is named after the prophetess Deborah. She was a prophetess of Judaism and is famous for being the fourth judge of pre-monarchic Israel. Now, we don't know exactly when she lived, but historians estimate that she lived somewhere around 1200 to 1125 BC. And she is also known as being the only female judge who is mentioned by name in the Hebrew Bible. And her most famous contribution to the Hebrew Bible is her Song of Deborah, which is recounted in the book of Judges, chapter 5, that covers verses 2 through 31. And it was specifically one of these verses in the Song of Deborah that inspired the concept of the Deborah number. And that is in chapter 5, verse 5 of the book of Judges. Now, obviously, the book of Judges was written in biblical Hebrew, and it requires translation to modern English. And there are many ways to do that translation. The specific translation that inspired the concept of the Deborah number is shown here, where she says, "The mountains flowed before the Lord." And the idea is that if we as human beings take a hike on a mountain or go skiing on a mountain, we do that with the implicit understanding that the mountains are not going to flow underneath our feet. So the mountains are considered to be static, and we traverse hiking across the mountains or skiing down the mountains, believing that the mountains are not going to flow underneath our feet. And most of the time, that is a pretty good assumption. However, plate tectonics is a scientific fact. This was something that was highly controversial in the field of geosciences for a long time, but it is now proven that continents flow, mountains are created, they move over time, they decay over time. And the problem is that we cannot observe this directly as human beings because the time scale over which mountains flow is so much longer than our individual lifespans. So if we live on the order of 100 years, that is not nearly enough time in order to observe these geological flow of mountains. And therefore, we would need to be able to observe the mountains on a much, much longer time scale that's not accessible to us as humans, but would be accessible to the Lord, who for whom any amount of time can just go by in a flash. So the Lord is able to observe the flow of mountains because he can observe on any arbitrary time scale, including those time scales that are orders of magnitude longer than the time scales that are available to us as mere mortals. Now, jumping ahead, the specific talk that inspired the concept of the Deborah number or introduced the concept of the Deborah number was done by Marcus Reiner. Marcus Reiner was an Israeli physicist, and he visited the United States for a while. And during one of his visits, he gave an after-dinner talk following the dinner at the Fourth International Congress on Rheology, which took place in Providence, Rhode Island. That was back in 1963. Um, Everything from his talk was, written down, and it was published the following year in 1964 in Physics Today. And so nowadays, when people want to learn about the Deborah number, they will consult this paper in Physics Today. Now, one of the things that I love about this paper, probably because it comes from an after-dinner talk, is that it opens with a really interesting and humorous story. Now, when Reiner first came to the United States, he came to my state here of Pennsylvania, although a couple of hours to the east in the Allentown area, where there are other towns that have biblically inspired names, like Bethlehem, for example, which is the home of Lehigh University. And this is what Reiner wrote at the beginning of his paper, or at the beginning of his talk, that in 1928 I came from Palestine to Easton, Pennsylvania, to assist Eugene Cook Bingham at the birth of rheology. I felt strangely at home. There was Bethlehem quite near, there was a river Jordan, and a village called Little Egypt. The situation was, however, also slightly confusing. To go from Bethlehem to Egypt, one had to cross the River Jordan, a topological feature which did not conform to the original. Then there were here places such as Allentown, to which there was no analogy. And this could lead to strange situations, such as when a girl at school was asked where Christ was born and replied, "In Allentown." When corrected by "No, in Bethlehem," she remarked, "I knew it was somewhere around here." Now, if we look at the right-hand side here of Reiner's paper, this right-hand column is where he actually introduces the concept of the Deborah number. And he denotes Deborah number by the capital letter D. And he's defining this as being the ratio of the time of relaxation over the time of observation. In other words, if we write this out as shown here, the Deborah number is equal to some sort of an internal relaxation timescale. So how long does it take for a fluid to flow? Or how long does it take for some internal process of the system to take place? There's going to be some timescale associated with that. So that is in the numerator. And in the denominator of the fraction, we have the observation timescale. So if you are observing this process take place, what is the timescale over which you are observing the process? So the numerator here is a quantity that is intrinsic to the system you are studying. It is a timescale that is associated with the process that you are studying, whether it is fluid flow or any other process that is under study. Then the denominator is how long are you actually observing that? And this could be direct observation by you as a human being. Say you're observing some system on a time scale of seconds or minutes or hours. Or the observation time scale could be something that is shorter or longer if we have the appropriate scientific instrumentation to make those measurements on a much shorter or a much longer time scale. So, getting back to this verse that inspired the Deborah number, the mountains flowed before the Lord, what if we consider the time scale over which mountains flow? So in the numerator here, this would be a geological time scale. This is, 10 to the large number of years that it takes for mountains to flow. And this number in the numerator is much greater than the number in the denominator. The time scale in which we're hiking on a mountain or skiing on a mountain is maybe minutes, hours, days. And so this number in the denominator is much smaller compared to the time scale over which the process actually occurs. So as a result, we have a large number divided by a small number. So the Deborah number in that case is a very large number. Now let's apply the Deborah number to the concept of the glass transition. The glass transition is the fundamental physics that governs how we get glasses in the first place. Glasses are made by cooling a liquid so fast that it doesn't have time to crystallize, and the liquid structure moves around more and more slowly until it gradually becomes frozen into a solid-like configuration. So the conventional way to get glass is to start up here at high temperature. So we've got temperature on the x-axis and either enthalpy or volume on the y-axis. And if we start in the equilibrium liquid state at high temperatures, the liquid is flowing relatively fast compared to our time scale. If the liquid is flowing fast, that means that it only takes a small amount of time for the liquid to flow compared to the observation time. So we have a small number divided by a large number, which means that the Deborah number for the liquid is less than 1, or in other words, less than unity. A Deborah number that is less than unity means that the process that takes place, in this case, the flow of the liquid, is happening faster than the time scale over which we are observing it. So we observe the system as a liquid because we are keeping track of it for a long enough time scale to observe it flowing. Now, if you take this liquid and you cool it down, if you lower the temperature of this liquid, we're moving leftward on this graph as the temperature is lowered. The viscosity of the liquid is increasing. It's increasing by orders of magnitude. So it's becoming thicker in colloquial terms, going from something that maybe is like flows very easily, like water at room temperature, to something that's more like honey, and so on. So as the liquid is cooled, the viscosity is increasing. As the viscosity increases, the intrinsic timescale for that flow is also increasing. So as the liquid is cooled, the viscosity increases by orders of magnitude, and this internal timescale is increasing by a commensurate amount. This is also increasing by orders of magnitude. Eventually, the numerator here of the Deborah number comes of the same order as the observation timescale. When that happens, then we have a number in the numerator that is about equal to the denominator, which means that this fraction here is about equal to 1. Now, when that happens, that is the definition of the glass transition. The glass transition occurs when the kinetics of the liquid state, when the flow of the liquid is happening on a time scale that is roughly equal to the observation time scale. So in other words, it's taking roughly the same amount of time that we're observing the system for the system to flow. And if you continue to cool the system, the numerator here continues to increase, and it's going up by orders of magnitude. Our observation timescale is staying the same. This is still the same timescale that we are observing the system in the laboratory, but because the system is becoming colder, the viscosity is increasing by orders of magnitude, and now it's taking longer and longer for this liquid to flow. And therefore, what we're doing is effectively capturing a kinetically frozen state that even if we are observing the system, say, on a time scale of hours, but what if it takes weeks for it to flow, or months, or years, or millions of years? Then we're not giving ourselves enough time to observe that flow. And so what we are observing is kind of like a frozen in snapshot of the liquid, where it is now behaving like a solid because we are observing it, we're interacting with it on a time scale that's so much shorter than the time scale that the system needs to flow. And that is fundamentally the definition of the glassy state. The glassy state occurs when the liquid is cooled to a low enough temperature that it avoids crystallization, and the flow of that liquid becomes so long that it is behaving like a solid, and that is the glassy state. And the glass, has some properties that are like a liquid, it has some properties that are like a solid, and it has some of its own unique properties as well. If you're interested on comparing glasses to whether they are liquids or solids, I have a separate video on that on my channel, which you are welcome to check out. But you can see what's happening here is during the glass transition, we're starting off with a Deborah number that is less than 1. As we go through the glass transition occurs where the Deborah number is roughly equal to 1. And then in the glassy state, the Deborah number becomes greater than 1. So this is why the Deborah number is one of the most important quantities in the field of glass science. And it is fundamental to understanding the physics of the glass transition itself. Now, the Deborah number itself is a kinetic quantity. It is based on timescales. It's based on the relative timescale between how much time does it take for a process to occur versus the amount of time that you have to observe the system. Now, even though it is a kinetic quantity, it has profound consequences on the thermodynamics of the system. For example, the graph here on the right shows the heat capacity curve of glycerol, which is a simple organic glass former. You'll see the heat capacity on the y-axis versus temperature on the x-axis. And if we start here at high temperatures, this is the liquid state. The liquid is flowing fast compared to our time scale of observation, so this indicates a Deborah number less than 1. Now, as the liquid goes down in temperature, it is increasing in viscosity, and eventually there is a rather steep drop here in the heat capacity of the liquid. This corresponds to the glass transition range of the liquid, because here in this glass transition range, the Deborah number is roughly equal to 1, which means that the liquid is no longer able to explore all of its different configurations because it's not able to flow freely. And so as a result here, there is a loss of heat capacity. The heat capacity of the liquid drops down as it is cooled through the glass transition because the configurational degrees of freedom of the liquid are being lost. This liquid is gradually being frozen into a subset of configurations. As that happens, the configurational contributions to thermodynamic properties like heat capacity are lost. And as the system continues to cool, the Deborah number becomes greater than 1. And then we get a solid-like response of the glassy state, where you can see the heat capacity of the glass is much lower than that of the liquid. This is because there are two contributions to the heat capacity of the liquid. There is the vibrational contributions, which is the atoms are vibrating, and then there's the configurational contribution, which is based on the liquid being able to flow and adopt different atomic configurations. As the liquid is cooled through the glass transition, it's still vibrating, but it's not allowed to flow to explore all those different configurations. So as a result, the configurational contribution to the heat capacity is lost. And down here at low temperatures in the glassy state, almost the entire contribution of the heat capacity is due to vibrations. So even though the Deborah number is a kinetic quantity, it has major implications on the thermodynamics of the system because of the loss of these configurational degrees of freedom. The other thing that's interesting to note from both a physics and more of a philosophical point of view about the Deborah number is that there are really two ways to induce a glass transition. So if the glass transition is fundamentally where we undergo a transition of having a Deborah number of around 1, the conventional way of inducing that glass transition is to increase the numerator of the Deborah number while keeping a constant denominator. In other words, by lowering the temperature of a liquid, what we're doing is we're increasing the numerator here because the internal time scale is becoming higher and higher as it takes more time for the liquid to flow. So as the numerator increases, we go from a Deborah number less than 1, pass through the glass transition range where the Deborah number is about equal to 1, and then into the glassy state. This is the conventional way of forming a glass by, say, take a melt out of a furnace and then rapidly quench it. This is the standard way of getting a glass. But there is another way that a system can undergo a glass transition, and this would be instead of changing the numerator, we keep a constant numerator, but we decrease the denominator. We lower the observation time. So imagine if you have a liquid, and if you probe the liquid on a relatively long time scale, it's going to flow in response to whatever perturbation that you're introducing into the liquid. However, if you take that same liquid at the same temperature and you start perturbing it at a higher and higher frequency, as you increase the frequency of that perturbation, eventually the Deborah number is going to go through 1 because the time scale at higher frequencies, the time scale of observation is lower. And so the Deborah number will pass through unity as a result of lowering the denominator instead of increasing the numerator. This is used in a lot of spectroscopy experiments, such as specific heat spectroscopy, where a liquid, say around the glass transition region, is exposed to a spectroscopic stimulus that where the frequency varies, and over lower frequencies, where there is a longer observation time, it will behave like a liquid. However, as the frequency increases, then we're observing the system on a shorter time scale, and then the response becomes solid-like. So this is a way of inducing a glass transition as a function of frequency, which is related to 1 over the observation time. So two ways to induce the glass transition. One is by increasing the numerator here while keeping a constant denominator, and the other way is to decrease the denominator while keeping a constant numerator. They both have the same impact on the Deborah number, and therefore they can both induce a glass transition. So at the end, I'd like to point out that in Reiner's talk here in his paper, he not only had a nice joke at the beginning, but also at the end. So I would like to conclude with this a final couple of paragraphs from Reiner's paper, where he writes, "There is a story they tell about two students of theology. They were praising the Almighty God. Said one, 'For God, 1,000 years are like a minute. And as he is the creator of all, $1,000 are for him like a cent.' Said the other, 'Wonderful. Next time I pray to God, I shall pray, God, give me a cent.' Said the first, 'What will it help you?' He will say, 'Wait a minute.' This man did not take care of the difference between God's and his own timescale. And this is the connection between rheology and theology. And every problem of rheology, make sure that you use the right Deborah number." So that's it for today's talk. I hope you enjoyed this. If you have any questions or insights, feel free to leave a comment below, and I will see you next time.